So now that we have this idea of shielding and we can talk about the differences in the radio probability distributions, we can consider more completely why, for example, if we're talking about lithium, we write the electron configuration as 1s2, 2s1, and we don't instead jump from the 1s2 all the way to a p orbital. So the most basic answer that doesn't explain why is just to say, well, the s orbital is lower in energy than the p orbital. But we now have a more complete answer, so we can actually describe why that is. And what we're actually talking about, again, is the z effective. So the z effective felt by the 2p is going to be less than the z effective felt by the 2s. And another way to say this, I think it's easiest to look at just the fact that there's some probability density very close to the nucleus. But what we can actually do is average the z effective over this entire radio probability distribution. And when we find that it does turn out that the average of the z effective over the 2p is going to be less than that of the 2s. So we know that we can relate z effective to the actual energy level of each of those orbitals, and we can do that using this equation here, where it's negative z effective squared RH over n squared. We're going to see that again and again. And it turns out that if we have for example, for S, a very large z effective, or a larger z effective than for 2p, and we plug in a large value here in the numerator, that means we're going to end up with a very large negative number. So in other words, a very low energy is what we're going to have when we talk about the orbitals. The energy of the 2s orbital is going to be less than the energy of the 2p orbital. Another way to say that it's going to be less, so you don't get confused with the fact that this is in the numerator here, there is that negative sign, so it's less energy, but it's a bigger negative number that gives us that less energy there.